Parallel circuits practice. For each of these diagrams, you need to create a VIRP chart to be able to solve for each variable. If an ammeter or a voltmeter is present in your circuit, we also have to state what they are actually going to read based on the location they are at. All right, so we're going to go in order, starting with number 1. For number 1, we have a battery and 3 resistors. So we're going to create a VIR chart. Let's go with purple. And we have 3 resistors. So we have R1, R2, R3, and of course we need REQ. We also are solving for V, I, R, and P for each one. All right, so let's go through and fill it in. So for number 1, they tell us that we have 55 volts. That is our total voltage. So we can go ahead and we can label 55 volts right here. They also tell us that we have 5, 10, and 12 ohms. So we have 5 ohms, 10 ohms, and 12 ohms in our circuit. All right, so at this point, we go through and we can create our chart, or not create our chart, we can solve for everything that is missing. Let's solve for our total REQ. First, get the fractions out of the way. Our formula for parallel circuits is 1 over R1 plus 1 over R2 plus 1 over R3 because we have 3 resistors here. So we end up with 1 over 5 plus 1 over 10 plus 1 over 12. Make sure when you are plugging this into your calculator, you are using parentheses. 1 over 10 plus 1 over 5 plus 1 over 12. Doesn't matter the order you do it. Math is, or addition is commutative, so it doesn't make a difference which way you go about it. And we end up with 1 over REQ equals 23 over 60. If you did this and got a decimal, the 0.38, always make sure you go ahead and just do a fraction. You don't want to round anything. Rounding is the very last step. So always put it in a fraction or use the entire number with all of those 3's there. It's totally up to you. But you don't want to round, even if it's 2 or 3 decimal points. Because we're solving for REQ and not 1 over REQ, we do need to take the inverse of our answer. So I'm going to raise our answer to the -1 power, and we should get 2.61 ohms total. So 2.61 ohms as our total resistance. This is also a parallel circuit. So in a parallel circuit, we know that I have a constant voltage, so 55 volts everywhere. Solving using V equals IR for this column right over here, we can go ahead, and as we go down the list here, we end up with 55 divided by 5, so we get 11 amperes for R1, 5.5 amperes for R2, and 4.58 amperes for R3. Solving for our total resistance, we end up with 21.07, that's a 0, amperes. Solving for our last column, we're going to use power, and I'm going to choose to use P equals VI or IV. You could use V squared over R, you could use I squared times R. I'm just going to keep it simple and solve for all of our powers here. So for the first, we get 605 watts, 302.5 watts for R2, 251.9 watts for R3, and 1,158.85 watts for our total power. Okay. If we now go back, whoops, I want to get rid of the entire thing. If we go back and look at number 2, the only difference here is that we have some new values. So let's go ahead and solve for those. Again, we're going to create our chart. Each one of these questions, you should have created your own chart for. VIRP. We can go through and add in what we have. So we have our total of 12 volts. And we're going to go a little faster this time. And because we have the parallel circuit, we know that we have 12 volts everywhere. Your voltage is constant. We have 2, 4, and 3 ohms. So 2 ohms, 4 ohms, 3 ohms. Our total resistance, 1 over Req, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. This is probably where we need the most help in terms of the fractions. Or perhaps you're really good with the fractions, and that's also great. As you go through, again, you're putting your parentheses around your values. So we have 1/2 plus 1/4 plus 1/3 is equal to 13 over 12 as 1 over Req. Again, we want to make sure that we are taking the inverse of this value here. And we end up with an answer of 0.92 ohms. Makes sense because R1 is 2 ohms. So we know that our Req must always be less than, let me write that for you. It must always be less than my smallest individual resistor because we're talking about fractions. So if we run down this column right over here, we're going to use V equals IR. And like I said, I'm going to go through this a little bit quicker because we should at this point know how we're going and doing the math, right? So V equals IR, we should get 6 amps for R1, 3 amps for R2, 4 amps for R3, and then 12 divided by 0.92, we should end up with around 13.04 amperes. If you go through and you add up all of your individual resistors, you would have ended up with 13. So remember, we're rounding, so that's fine. For this column right over here for power, I'm going to use P equals VI as my formula. So 12 times 6. The first, we end up with 72 watts. This second one, we end up with 36 watts. 12 times 4, we end up with 48 watts. And then 12 times 13.04, you should have ended up with 156.48 watts. Looking at this third picture here, we haven't had any ammeters or voltmeters up until this point. So now if we look at this third picture, we do have a couple of ammeters and voltmeters. That we don't have to worry about until the very end because all we're doing is trying to solve. So we can go ahead and create our diagram. So we want to go ahead and we want to create it's probably easier if we just start from scratch real quick. If I can get a hang of how to use this pen. There we go. Way easier than what we were just doing. All right, so for number 3, we have 2 resistors, which means that we have to have R1, R2, and Req. Oh, goodness. We have V, we have I, we have R, and we have P. I did leave some space there, that's fine. All right, so looking at this picture, we have our total of 12 volts, and again, this is a parallel circuit, so all of our voltage is constant. We also have 18 ohms as our first resistor. We have 8 ohms as our second. And we can go ahead and we can solve for our total resistance. Again, This should seem repetitive to you because we've got to make sure that you are practicing this, that you know how to do this, and that it's very easy for you to do this when it comes time for us to have these questions on the Regents or on any kind of class or exam or quiz. So we go ahead, we solve for this here. In parentheses, as always, 1 over 18 plus 1 over 8. You end up with 1 over REQ equaling 13 over 72. We go ahead and we take the inverse of this because at this point we know that that's what we have to do. And you end up with 5.54 ohms. So 5.54 ohms. Solving for this column right here, again, we're going to use Ohm's law, so V equals IR. So we have, for the first, 0.67 amperes, 1.5 amperes for R2, and lastly, for our total current, we have 2.17 amperes. For this column, again, I'm going to use P equals VI 12 times 0.67. You should have ended up with 8.04 watts. 12 times 1.5, you end up with 18 watts. And 12 times 2.17, your total power, 26.04 watts. All right, moving right along. Number 4. Oh, actually, not moving right along. I skipped over this part. So now the question becomes, what is going to be read from A1, A2, and V? All right, so let's start with V because that one's the easier of the two. When we're looking at the voltage, the voltmeter for this voltage right here, we see that it is only around the 8 ohms. So we look at 8 ohms, we go to see what voltage is associated with that 8 ohms, and that gives us obviously 12 volts. However, like I said, this is a parallel circuit. So did we really have to do that? No, because we know that voltage in a parallel circuit is constant. So no matter where you are, you should always be reading 12 volts. This is, again, a parallel circuit. Your ammeters are a little bit different. So when we look at A1 and A2, we look first to see what kind of paths they could possibly take. So let's look at A2 first. So if we look at A2, A2 is right over here. A2, as you travel around your circuit, you always want to get back to your battery. You're not going to be able to go and kind of like work backwards. So as you travel, you're only going to be taking this path all the time, starting from this point A2. There is no way for it to travel up the 18 ohm resistor, which means that A2 is only going to read the current flowing through the 8 ohms. So we look at 8 ohms, we look at 1.5 amperes, and that is the value that is associated with A2. So for A2, we have only the 1.5 amps based on the placement of A2. Now, if you look at A1, as you start here, has the ability, once it starts to move, once the charge starts to move, to either make a turn at this point or continue on and make a turn right over here. So it has the opportunity to pass through both resistors. And because it has the opportunity to pass through both resistors, this current is going to read the total current in your circuit, which for this problem has to be, or happens to be, 2.17 amperes. So all in how it's placed, the ammeter is placed in your circuit. If we look at number 4, this question right here has 3 resistors. So we're going to make our diagram quickly, also indicating our REQ down here. We have V, we have I, we have R, and lastly, of course, P. All right, so let's go through, fill this in. We have 110 volts total. We have 10 ohms, 20 ohms, and 40 ohms for each individual resistor. I know that this is a parallel circuit, so I can go ahead and I can fill in I can go ahead and fill in all of my voltages here. They're all going to be the same. All right. I can then go ahead and solve for my total resistance. 1 over Req is equal to 1 over 10 plus 1 over 20 plus 1 over 40. If you solve for this, again, using parentheses as always, you are going to end up with, 1 over 10 plus 1 over 20 plus 1 over 40. You end up with 7 divided by 40 is equal to 1 over Req. Always remember to take the inverse of your answer. So taking the inverse of our answer, we end up with 5.71 total resistance. 5.71 ohms. Now we can go ahead quickly and we can solve for VIR for this column, as well as P equals VI for this column. So let's go through and do this to see what we get. So for the first R1, we end up with 11 amperes. We ended up with 5.5 amperes for R2. We end up with 2.75 amperes for R3. And lastly, for our total current, we end up with 19.26 amperes. Solving for our total power, let's work backwards actually. If we want to solve for our total power, why not? We end up with 2,118.6 watts. Keep it interesting. Let's work backwards like we said. So R3, we end up with 302.5 watts. We end up with 605 watts for R2. And lastly, for our R1, we ended up with 1,210 watts. Now, if you look at where your placements are for your ammeters, we look at A4. These are just labeled as just A4, A7, and A8 just because they're labels. They don't go with any particular, the numbers don't mean anything. It's just the way that I labeled them. So we look at A4. A4 has the ability to travel down 1, 2, and 3 paths, which means that it's going to read all 3 currents. It's going to read 19.26 amperes. If we look at A7, well, A7 starts over here. So we're able to go down 1, 2 paths such that we can end up back at the battery both times. Again, we're not going to go backwards. We can't decide that we're going to go up some random path and go to A4. That's not the way it works. So this A7 only has the ability to read both R2 and R3's current. So that will give us a total of 5.5 plus 2.75 to give us 8.25 total amperes. Lastly, A8. Well, A8 is all at the end, and A8 only has the ability to read this one resistor at the end here, which is going to be R3, which is 2.75 amperes. If we look at number 5, again, we have a parallel circuit. We have all of these different ammeters placed here. So let's go through, let's create our circuit VIR chart. Let's get rid of some of this information down here. Whoops. Oh, I do not want to paste it. Get rid of you. And let's go back down here. And let's get rid of this. All right. So now we're looking at number 5. Number 5 has 1, 2, 3, 4 resistors. So we do have to make sure we include them all here. So 1, 2, 3, 4, as well as Req. Okay. V, I, R, and P. All right. We can go through and we can label what we know. So we know that we have 50 volts everywhere in our circuit because, again, this is a parallel circuit. That is a 5. I don't know why I draw them like that. Okay. We also know that we have 20, 10, 20, and, oh, I forgot an ohms there. There we go. 5 ohms. So what did I say? We have 20, 10, 20, and 5. So we have 20, 10, 20, and 5 ohms. All right, so let's do this. So we are starting out with, as always, 1 over Req. We have 4 of these resistors to work with. So we are going to solve for this first. 1 over 20 plus 1 over 10 plus 1 over 20 plus 1 over 5. When you plug this in, again, as always, we are using parentheses. 1 over 20 plus 1 over 10 plus 1 over 20 plus 1 over 5. We end up with 2/5 equals 1 over Req. That was 2/5. Take the inverse of that, and you should have ended up with an answer of 2.5 ohms. All right, so 2.5 ohms total. We're going to go through, we're going to use V equals IR for our column here for our currents, and we're going to solve for this. So we should have ended up with 2.5 amperes. We should have ended up with 5 amperes, 2.5 amperes for our third, 10 amperes for our fourth resistor, and I do believe we should have ended up with 20 total amperes. If we go ahead and we solve for our power, if you did this correctly, you should have ended up with 125 watts, 225 watts, 125 watts, 500 watts, and 975 watts. This is actually supposed to be a 5. I don't know what I'm speaking and writing, 2 different things. So this is what number 5 should have looked like. Lastly, finally, number 6. Actually, before we continue on here, let's look at this for 1 second. Okay, so this A right over here, this A, has the ability to travel down 1, 2, 3, 4 paths, which means that this A is going to read our total resistance, our total current. And our total current we found to be 20 amperes. This current, this ammeter right over here, only is able to read this 20 ohms and this 5 ohms. Remember, we can't work backwards. So we have to look to see, well, what did 20 ohms and what did 5 ohms both measure? Together, they measured 12.5 amperes. Lastly, for this third picture right over here, we have 3 resistors. So we have 3 resistors. Let's see if we can just erase some of this here. Bear with me. You're for sure running out of space. Oops, all right. Only lost 2, but that's totally fine. All right, so if we go back and we look now to see what we are working with, for number 6, we have a total of 36 volts, which means, again, this is number 6. I know that we're kind of going back and forth here, but that means that we have 36 volts for our entire voltage column because voltage is constant in a parallel circuit. We then have 6, 9, and 12 ohms. So 6, 9, and 12 ohms. we can go ahead and we can solve for our total resistance using our equation here. We have 3 resistors. Okay. We have 1 over 6 plus 1 over 9 plus 1 over 12. Plugging into our calculator, we end up with 1 over 6 plus 1 over 9 plus 1 over 12. We end up with 13 over 36. However, we know that we have to take the inverse of this to get our final answer of 2.77 ohms. So, at this point, you know the drill. We can go through and we can solve for all of this here. So, for R1, we end up with 6 amps. 36 divided by 9, we end up with 4 amps. 36 divided by 12, we end up with 3 amps. 6 plus 4 plus 3, that should give us around 13 amperes total. Solving for our power, we end up with 216 watts for R1. For R2, you should have ended up with 144 watts. 36 times 3 for R3 gives us 108 watts. And 36 times 13 gives us 468 watts total. Finally, we look at our diagram here and we see that we have 3 ammeters. These ammeters are placed in their location because these ammeters, based on where they are, only have the ability to read the currents that they're right next to. Remember, you can't go back. So if you're talking about this current right here, you're not able to kind of go back and do some weird path. That doesn't work for us. So with that said, these currents, or these ammeters rather, are going to read 6 amperes, 4 amperes, and 3 amperes. All totally based on how we solved using our chart.